So excited to have you all here with me today for this tutorial. My name is Rebecca, and potentially some of you have seen me doing this in a data science tip video on LinkedIn. I'm working to try to build kind of a global community of data scientists who are all working on similar kinds of problems. And collaborating to try to get past the hard parts of our jobs and become more successful together. Today's speaker, it's my great honor to introduce you to him. So for anybody out there who is wishing that their machine learning models were more adaptable, that they could be more flexible, that they could adapt to kind of changing conditions, new requirements, changing data, I think you are going to be very excited to learn from our speaker today. So our speaker today is Dr. Benjamin Bangfort. He is a distributed systems expert whose career has focused on planet scale, huge scale. So the scale of the people who are participating in this tutorial today all over the globe. He has specialized in these kind of planet scale data systems that can quickly adapt to change. He is an author of 2 O'Reilly books. I don't know if you've read those books that have the red books that have the animals on the cover. Actually, if you look behind him, you can see a couple of them over his shoulder. So he is the author of 2 O'Reilly books, and he's also the faculty director at Georgetown University's Data Science Certificate Program. And he has been for almost 10 years now, I think. He is also the CEO of Rotational Labs. If you don't know about Rotational Labs, that's also where I work. Rotational Labs is a company that helps teams implement real-time data products, right? Products that connect us around the world, that have real kind of data flowing through them, and people who are building things with that data that need to kind of be flexible and need to adapt. And need to be robust and need to be deployable. So Benjamin is also the most prolific programmer that I have ever met. He has written software for everything from security and networking to machine learning visualization and natural language processing. I've known him for years. He is a fantastic speaker. And so I know that we are all in for a treat today. And with that, I'm going to pass it over to you, Benjamin.
Thank you so much, Rebecca, for that lovely introduction, and welcome to everyone from all over the world. I'm so glad that so many people are interested in rethinking MLOps and learning a little bit more about how to get our models into production and make them available to our users, which I think really is the end goal for all of us, of course. So I've got a proposition for you all today, and the proposition is I'd like us all to start rethinking machine learning operations in terms of data flows. And I'm going to talk about data flows in 3 ways during this webinar. The first is thinking about data flows enhancing our hypothesis-driven development process and being able to create reproducible training, more explainable models. I'm going to start thinking about async inferencing and how we as data scientists can interact with the rest of our colleagues and the other teams in our organizations without having to worry about the challenges of code or microservice or DevOps implementations, and using data flows as that communication layer. And then finally, we're going to talk about how our models behave in the wild when they're being used by real users, and how do we monitor their behavior? How do we trigger retraining, and how do we understand when models need to be changed or adapted? And I think that the central theme for all of this is going to be the theme of data flows, which will have the effect of enabling us to do more real-time data science, become more engaged in our organizations, and more engaged with our users, which I think is something that we are all very interested in. So Adam Bellamere wrote a book called Event-Driven Microservices. And in the first chapter, he talks about organizations and how the communications of organizations affect the systems that they build. And he used Conway's law, which is here, as a motivator for that idea. In 1968, Conway wrote, organizations which design systems are constrained to produce designs which are copies of the communication structure of these organizations. And Conway used that as an argument to say why, committee-based invention doesn't really work. But I'm going to use that as a segue into thinking about what is the issue with MLOps right now? Why do we need to rethink MLOps? And I'm going to lead us off with kind of a shocking statistic that was published in VentureBeat by a panel of folks from IBM and other big tech companies who cite the statistic that 87% of data science projects never make it to production. Now, to me, that's a shocking number, but I think that potentially we're all feeling that number right now. Right? In the past, there was sort of a data science boom, and it felt very easy to get hired and very easy to maintain high salaries. But now it seems that data science teams are struggling to make an impact in their organizations, and this could be the cause of that. And for those of us who are data scientists, it's a existential threat, right? We do have to figure out how to get our projects and our models into production. And I think that's why everyone's here today, right? We want to make sure that we can deploy models to our users. But probably all of you are wondering why? Why do only 13% of our models make it into production? And the panelists propose sort of 3 reasons, right? So the first is a commercial culture, right? The culture of leadership and a style of product development that happens in non-academic organizations, right? The science part of data science is there for a reason, right? We use hypothesis-driven design, we use experimentation, failure is common, but that's not how organizations work, right? When you're building a product, you want low-risk things, and so leaders might not be willing to put models into production that have F1 scores of 0.61 or coefficients of determination that are too low. Whereas, that culture will then start to isolate the data science team because they're not able to push their projects towards the application. You also have disconnects between roles and responsibilities, right? You might have a DevOps team, a software engineering team, a product development team, a front-end team, and they might not be integrated with the data science team. So they might not have any impetus or desire or motivation whatsoever to build your models into their product or into production. And so we see Conway's law loud and clear right there in commercial culture, right? If you have that type of organization, then you have no ability to communicate your data or your work to other teams in your organization. I think the second point, though, we're all really familiar with, right? Data silos. Where's the data? We can't train a model if we don't have the data. And I think that we as data scientists do a lot of sitting around or a lot of data engineering, waiting for data to come in, waiting for that data to be made available. And that's a huge problem to affect our work. And finally, there is the lack of collaboration, which I had already suggested, right? The disconnect between the folks who are stewards of the data, the software engineering team, the DevOps team, and the data science team really creates that problem of ensuring that these models go to production. So what I think that we need to do as a group is to understand how to augment our hypothesis-driven development workflows, right? So hopefully everyone is familiar with the model selection workflow, where we're taking our initial data and we're composing these model triples of feature engineering, algorithm selection, hyperparameter tuning, and we're looking for the simplest, most predictive model that fits that data. And we need to take that and we need to augment it with machine learning operations. So this is kind of the what is MLOps. MLOps is about taking trained models And usually applications are suites of many models. So incorporating them in some sort of model management system. So we understand what models are being used, when and where. Creating explainable applications, right? It's not just about inferencing. It's about being able to give reasons or explanations or understand that inferencing, especially in a model application where you're not going to have 100% correct answers all the time. In fact, if you could, then you should develop a heuristic algorithm and not a machine learning model, right? So we want that sort of fuzziness in our machine learning applications. But that fuzziness also gives us the opportunity to monitor how those models are behaving and retrain them and get feedback and strengthen our models, right? And so, what I'll talk about later is we really do want to get weak models into production and strengthen them over time because they are being used and explained in our application. And the only way to do that is to augment hypothesis-driven development with machine learning operations. So this proposes this sort of question: how do we increase our effectiveness as data scientists without taking on the engineering responsibilities of other teams? Data scientists are jack of all trades generalists, right? They have a lot of different skills in a lot of different areas, but I am certainly not suggesting that everyone on this call, in addition to their responsibilities of understanding models, interpreting models, training models, doing data analysis, and sort of the software engineering required for data analysis, I am not suggesting that you also take on the responsibility of DevOps and application development and product development. Those are the responsibilities of other teams. So we need to increase that effectiveness without taking on those responsibilities. And so what I propose is that if we focus on data flows, right, we can increase that collaboration with those other teams without interrupting the processes of the other teams in our organization, and while ensuring that our work gets immediately made available to them so that they can incorporate it in their agile development or whatever they're doing. And so the decoupling effect here is that if you have data engineers or data stewards who are maintaining these databases, and they're probably very protective of those databases because you don't want bad data in those databases. Instead of asking for data access or data snapshots, instead hooking up some sort of source to that data source, and you create an event stream that's read-only, that matches the security and privacy policies of that original data source without modification, that will allow you to stream data in from multiple generic sources so that you can start working with your hypothesis-driven development workflow. And then once you start creating models, what you want to do is you want to have the inference data streaming in that you want to make predictions on, and then stream that data out so that application developers don't have to worry about building a system from some code that you're going to toss over the fence, particularly if that code's written in Python or R and the application is written in Java or Go. So instead, it becomes all of these data flows, right? And using data-driven coupling rather than application type of coupling. So with that, we are going to rethink our ML operations for data flows.
So can I give you a couple of questions that have come up here, Benjamin?
Absolutely.
Okay, so first question, I think it applies maybe to the prior slide, or maybe yes, this one. Could you just say what is an event stream? Because it sounds like maybe the person asking the question has heard this term, but maybe not in a data science context before. And so could you just kind of give like a high level definition?
Absolutely. So an event stream is an alternative, I think, to databases where instead of executing transactions on a database that has a data store, what you do is you have publishers that publish these sort of atomic events, these atomic datagrams into the event stream. the stream totally orders those events, and then multiple consumers can read from that event stream in order. It is not the same thing as a time series database, right? We're not storing like an ordered sequence of telemetry, but rather these things are rich events that have this multiple publisher, multiple consumer model, where the event, the event stream or the event utility, things like Kafka, Pulsar, Ensign by Rotational are actually brokering. They're connecting the events from the data publishers to the data consumers.
Thank you. Okay, I have another question. And if anybody else has questions and you'd like to have Dr. Bengfort answer your question, go ahead and put it either in the chat or you can put it in the Q&A tool. So the second question is, it sounds like it's a use case question. The use case is manufacturing. And the data is an IoT kind of, it sounds like a event stream or a kind of a stream of events that are related to conditions in the manufacturing context. So maybe things like temperature and humidity and things like that, but also on the actual manufacturing devices. So the question is, in this kind of use case, if I'm new to data science and I'm trying to figure out how to think about how to optimize this manufacturing context. So we're producing something and we have all of these production parameters. And we know what the outcomes are, at least historically. So we can look at kind of historic, production parameters, and then look at the outcomes of like how many widgets were made. So how would you kind of take that context and translate that into kind of an architecture, like a machine learning architecture that could be operationalized, just as an example? Does that make sense?
It does make sense. In terms of use cases, I think that what we want to think about in terms of our machine learning architectures as they aren't single models, right? So no one single model will optimize any process, not even a manufacturing production process. So we do want to make sure that we are operating many different models that work together, right? So for example, you might have classifiers that are detecting ranges of performance for different pieces of machinery, right? Classifying them as like low, medium, high, learning the thresholds from your sensor devices. And then you can build those classifiers into higher level models to show whether groups of pieces of machinery are operating at high, level, high. Of course, anomaly detection is extremely important when it comes to processes in manufacturing, and being able to detect spikes in time series and using those spikes as events that propagate to other machine learning applications. In terms of what you need, you certainly need a time series database to be collecting all of this time, this information, but you're not necessarily going to be training models on that time series data, with the possible exception of time series analytics type models. But still, aggregation is really important in those. So you want to make sure that your time series database is also emitting streams of events that can be learned on by sort of your downstream hypothesis-driven development.
Thank you. I have another question, and I'm going to ask it, but it's possible that this is something that will be in your next couple of slides. And so if it is, let me know, and we can hold the question and kind of come back to it after the next section. So the next section is, or the next question, sorry, rather is, can you explain what you mean by model management here? So in this yellow kind of rectangle, the word model management is here, and that is, kind of one of the keywords in for the lecture today in the title. And so this person says, what exactly is meant by model management here? What does that include? Is this just things like model stores, or is the word meant to be larger and more inclusive?
Yeah, we'll definitely talk a little bit more about this. I think it is meant to be larger and more inclusive. So model storage is important, but it also means loading the model into applications and making inferences on it. It means ensuring that feature extraction workflows are connected to the right models. It means monitoring models over time and making sure that they're not degrading in their performance. It means including explainability, visual diagnostics and reports, and being able to explain inferences. And also about sort of routine cross-validation over time and re-annotation of data inside of the system. So model management is a little bit more of an inclusive term, and is something that is distinctly needed when you're juggling lots of different models for lots of different application outcomes, and those models have to exist in time, so you have to have them retrained and augmented. And we will get into that a little bit more as we get into the webinar.
Okay.
So we're going to think about MLOps for data flows in sort of three ways, right? So we're going to talk about reproducible training, async inferencing, and monitoring and triggering, which is where that model management piece will come from. So the first is reproducible training. Now, we're all data scientists, and the sort of scientific method does imply that reproducibility is important, but this is not an academic exercise. So this is not about peer validation or the scientific method. Instead, reproducibility is essential for explainability, debugging, and validation. Now, that explainability piece is really important. There has been some work in creating text-based descriptions for why a model produces a result. But those text-based descriptions are usually all rooted in the instances in which the model was trained, right? So if you think of a model as this black box that has some internal parameterized representation of the models that it was trained on, the way to understand why a model is making a decision that it is based on the training data. So that's where explainability comes from. And so if you trained a model 3 months ago, 6 months ago, 7 months ago, you have to have access to the instances it was trained on in order to explain why the model is doing what it's doing. And I think one thing that we really lack as a community is that explainability inside of applications. The other big thing is exceptionless exceptions or exceptionless errors, right? If we move a model into production and let's just say 2 columns get flipped in our feature table, that model is going to be perfectly happy to make an inference on that data, even though it could be that the scope or range of that field or feature is completely out of whack with the data that's getting put in. And so you're making these bad predictions, not on bad data, but you don't get an exception, right? You don't get an error or a stack trace or anything like that. And when it comes to debugging why a model is performing poorly, once again, you need to be able to retrain the model on the instances that it came from. And of course, you're going to want to perform cross-validation routinely over time. And if you are going to do that, you need to be able to rebuild your model, right? It's not enough to just snapshot a model and say, this is the thing that's going to last for time. So reproducibility is way more about than just saving a random seed or saving some hyperparameter arguments, right? It really is a data management problem. So speaking of data management problems, let's talk about the types of computational data stores that we use on a routine basis. And I think there are 2 main types. The first are transactional databases. These are the relational databases, Postgres, MySQL, Oracle, and then the columnar databases, right? Things like Cassandra, Redshift, and other sort of analytics-oriented databases. The nice thing about transactional databases is they are well suited to applications. So a lot of times data scientists find themselves using these things mostly because they are borrowing from an application that's going to, really only want to deal with a small number of correlated rows at a time. And the focus really is on normal forms and deduplicating data to make inserts and updates really fast. But now you see our first challenge with reproducibility is that in a transactional data routinely changes and you get no provenance information, provenance or versioning or history. And if data changes between the time that you train the model and the time that you want to reproduce the model, which is likely in a transactional database, then you've lost your reproducibility. I think data scientists prefer to use columnar databases because they are better at efficient aggregations, projected joins, and queries that read most of the database, which is what we're doing when we're doing machine learning. So they are a really nice format to use. Probably all of us are used to using columnar storage like HD5 and Parquet and other things because of that benefit. So columnar storage makes it really easy to append records and to perform transformations on features, right? Again, a very good tool for us. But it is really difficult to identify or modify individual records or even subset or sample rows. So when it comes to model reproducibility, the query performance on a columnar database is also not there either. Now, I'm not saying to not use these tools, right? But it does introduce the question of how do you identify the original instances that your model was trained on? How do you be able to make that explainable reference rooted in the instances and maybe come back and filter anomalies or filter bad data that's causing your models to perform bad? How do you do that? And I got to tell you, it's not just enough to store the ID of every record that exists in your training database because they're changing in the main database. Now, of course, you could spit out and snapshot all of your data into a Parquet file or HDF5 file or something like that. But now you have this sort of data management burden that becomes even more troublesome. So what we propose instead is using a tool called change data capture. So what change data capture is it's a tool that's actually part of most database systems. You'll usually hear it referred to as the write-ahead log inside of a database system. But change data capture is actually being lifted these days more to the user so that you can actually see what updates are happening in the database. So as the database is getting written to, it spits out these events, right? These event streams of these different transactions. And those are put into an event bus that can be read by different consumers. So going back to that question of what is an event stream, here is an event stream, right? You have all of these people writing to this database that is the publisher that produces all of these change events to the event stream that multiple consumers can read off of. So what change data capture does is it records all updates to the database in a specific order, and that preserves the history of changes that were made to the database. And these events can be consumed. One of the big things that change data capture is used for is for creating snapshots or for creating clones of databases. So that question of where does the data come from? Well, this is one way you can get the data without having to perform any transactions whatsoever on top of the live production database. If you can get access to the change data capture event stream, then now you are getting the data into your data science workflow, and you can create snapshots in your own local transactional database or your own local Cassandra or columnar database, right? You don't have to worry about the production database. But I think more important for reproducibility is that now, in order to identify the data set, all you have to store is two things, right? The start offset and the end offset. Because if you say, model A here goes from this event to this event, right? That's this stream of events that has occurred to make changes to this database. At the end of that time, you have a snapshot of a data set, and you don't have to store all of these independent data snapshots, right? Because you can see here, model A and model B share, at least two of the same events. So you store one sequence but you're able to reproduce your data set using the change data capture module. So the great news is that CDC and using event flows to monitor reproducibility and things allows you to easily join different data sources. It makes sure that you have read-only access, so you're not interfering with the production database. You can also create tombstone records for privacy preservation or anomaly removal, which still gives you the opportunity for reproducibility and explainability, but ensures that if you need to delete a record or if you need to keep things private for compliance reasons, you can. Hopefully everyone sees here that there's a big opportunity for data transformation pipelines once you get access to these event flows that will help you preserve your data wrangling efforts and operationalize those wrangling efforts so that they can be involved in sort of upstream machine learning operations.
So I have a good number of questions for you here. So it looks like there are a few that are sort of related. So I think that there's a lot of interest in hearing a little bit more about change data capture, or CDC. Is it kind of primarily a way to track data lineage? Or is it basically just like a generalization of the term Kafka stream? So somebody's asking, how should I think about change data capture, related to Kafka streams?
So you can certainly put a change data capture log into a Kafka streams, and Kafka is popularizing change data capture, right? So the way that you would consume the CDC log could be through a Kafka stream or a Pulsar stream or a NAT stream or an Ensign stream. But the database is producing those event logs and putting them into the stream. So you would consume them the same way you would consume any event stream. In terms of the question of lineage, so this will give you a history of changes made to an event. In order to maintain provenance and lineage, you would also have to insert data about who is making the change. And that is relatively easy to do inside of change data capture systems. Ensign, as an example, encodes geographic provenance. So where the change is coming from, like where in the world, and can include things like IP addresses and things to identify different users where these changes are coming from. And so it takes little effort to augment a CDC log into a data lineage log.
Okay.
But it's and before we go on to the next question, I will say, but it certainly gives you model lineage, right? You know where the model came from, exactly what data the model came from.
Thank you. So actually, I'm glad you said model again, because the next question I think is sort of somebody asking a question about the first section. Do you have any, so, this person is suggesting that there are some, it seems like there are some model management tools out there. What factors should we be considering when we're looking and evaluating these tools to know if they're really going to help with MLOps, or if it's just another thing I got to figure out that's not maybe going to help me. So how could I know if it was a good tool or not?
Well, I mean, that's a great question, and potentially one that I would have to think about a little bit more. I guess in the spirit of this webinar, my first question would be, does this model management tool enable communication across organizations and teams? Is it able to be part of different data flows? Am I able to ask questions of my models and monitor them over time? What does this tool do beyond model storage in order to ensure that the model is going to production, right? And so if it's a tool that you as a data scientist have to learn, but it makes it easy for your software engineering team or product development team to incorporate, then that would be I think a good model management tool. Whereas if it's something that both teams have to learn, then potentially that's less good.
Thank you.
And that is, do you have another question?
I don't see any, actually, we have one person with their hand raised, but if people could type their questions in the chat or the QA, I'll sort of aggregate them and I'll have another batch ready for you after the next section, Benjamin.
So speaking of sort of the problems of learning tools, I do want to move into this idea of async inferencing, and start with a story that was actually told on that panel that was reported on VentureBeat, the same panel that said 87% of data science projects do not go to production. So Chris Chapo, the Senior Vice President of Data Analytics at Gap, told this story about how one of their early data science projects, which created size profiles and could determine the range of sizes and distribution necessary to meet demand on both on their online stores, I think, and in their retail stores. And so the data science team had created this model, they had created this project, and they handed over the algorithm to an engineer on the product team who recoded the program, presumably from Python, into Java and implemented the program. 4 years later, they realized that it had been broken and it wasn't working the way that the data science team intended it to be used. So that's a terrifying story. And I hope the takeaway for all of you is that data science teams must be in charge of deploying and managing their models, right? Because A, we understand the models, we can debug the models, right? And we're the ones who will notice when something is going wrong. It won't be the product development team who will and should treat the model like a black box, right? I want a list of sizes so that I can do inventory management, right? I want a list of recommendations, right? I want some categories, I want the model to spit out these inferences, right? And that's how they should treat it. But we need to be in charge of deploying and managing them. Otherwise, this recoding process and things like that are going to be what happens. So that said, I think what data scientists are taught right now is, well, wrap your model up in a little microservice, right? Create a little API. We don't care if you use like Fast API in Python or Flask or something like that. Just create a little API and we will query that API and we will get them to you. So ignoring the fact that that does make you more of on the back end engineering side, let's talk about the perils that puts you into with microservice, right? So anyone who's written a lot of microservice APIs knows that the very first thing that you deal with is security and access, right? Who's allowed to access this API? Even if it's an internal only system, meaning it's not accessible from the internet, you're still dealing with things like IAM proxies, MTLS, authentication, etc. And frankly, those aren't data science problems. And if you're not good at them, you can mess that up really easily. The second major issue is scaling, right? If you have a Kubernetes deployment, then you're going to have to get this in Kubernetes, right? If you have an Elastic Beanstalk deployment or Heroku deployment, like how are you going to scale this thing up? And then what happens if you're going to put this in multiple regions, right? But even just beyond that sort of obvious scaling things, there's little things that happen, right? Like rate limits. How do you rate limit your application to make sure that you don't have cascading failures? How do you decide what amount of compute and memory per pod is necessary, right? That's a really hard question to answer, and probably a good data science problem if anyone's interested. But that's more on the DevOps side of things. Finally, when you're running these microservices, you do have to have observability and tracing, right? You'll need to know uptime statuses, logging, error handling, and performance metrics. You need those things because that's part of running a service in a production application. So I started this webinar by saying, we want you guys to focus on being data scientists and not also adding in the responsibilities of data engineering and DevOps and security and all of these other things. So what can we do? And I think the answer is to make inferencing asynchronous. So a microservice or any type of API is synchronous, right? A request comes in and then you have to make the response. What we can do instead is we can have the application publish an instance that needs to be inferenced onto an event stream, onto an instance stream. And then we just have to write some sort of application which listens to that instance stream, makes an inference, and publishes the result to some result stream that the application is then listening on. Now, this isn't a new model. If anyone's used Celery, right? You know, asynchronous tasks are something that happen, particularly for tasks that take a long time to run, right? Like sending emails is usually an asynchronous task. It's not usually an API call. And inferencing is actually one of those things that could take, you know, more than 200 milliseconds, which is the sort of standard for response times for APIs. So thinking about things asynchronously means that you have more opportunity to sort of connect to multiple applications with the same models. And if we think about the original story, if the application is written in Java, then they can connect to their instance stream using a Java SDK, right? Whether it's Kafka or Nats or Ensign, whatever, they use the Java SDK to connect to the instance stream. And then the code that you guys are writing, you can connect to the instance stream in Python, right? Use the Python SDK or the Watermill SDK, right? Use the tool that you want to use to connect to these instance streams. And now we've decoupled the application from the model. And if we want to add another application that also wants inferences, they don't have to think about the API and the security aspects. Instead, they can publish things either to the same or a different instance stream and get results the same way as the first application. So have I removed all of those concerns from the microservice perils? Of course I haven't, but I've separated them away from you as the data scientist, right? So the microservice perils still exist, but they are now delegated to the event bus, right? They're delegated to whatever that eventing system is that's in the middle, right? And the DevOps team can manage that just fine. That's what they're good at. That's what they need to do, right? So permissions on topics, right? Permissions on streams, who has access, scaling up the event bus, right? Multi-cluster scaling, rate limiting, all of that stuff is now the responsibility of the DevOps team, and you don't have to worry about it. All you have to do is be able to connect to the event bus. Plus, you can scale and maintain your processes independently, right? So if you want multiple lambdas reading from this event bus, you can use a consumer group to have multiple different lambdas doing the inferencing. You can easily swap out models in the backend without having to go through downtime or a version increment for the application. It does make managing that model in operation in real time much, much easier.
Okay, got another batch of questions for you, Benjamin. Okay, this is, I think, maybe more of a comment than a question, but it sounds like this is about the fine art of avoiding too much responsibility. So I'm not sure if you have any response to that.
Yeah, I mean, I think that is an important skill that many organizations don't understand, right? You want to delegate specialist responsibility to the specialists, and you want to aggregate responsibility via communication across teams. So yeah, you should absolutely avoid specialist authority that you are not a specialist of.
Actually, and this connects, I think, perfectly to the next question, which is, when it comes to roles. So if you're going to become like a machine learning engineer, and I think the implication here is that people are sort of assuming that what you're presenting here, the idea of doing this kind of event-based MLOps, is something that would be the responsibility of more of like a machine learning engineer. So maybe first of all, does that, is that a valid kind of interpretation? And then if you want to do that work, if you want to be kind of doing this MLOps work as an ML engineer, do you need to first be a data scientist so that you kind of understand the mechanics of what's happening?
My definition of data science is directed towards building data products, which to me is applied machine learning, right? So I personally don't distinguish between a data scientist and a machine learning engineer, with the exception of potential domain expertise. A machine learning engineer might be very good at machine learning in general, but a data scientist might have domain expertise in, say, manufacturing optimization, right? But the data science team will presumably have both machine learning engineers and data scientists and data engineers on it. So what I'm saying is that all of this is the responsibility of the data science team as a whole. It's not the responsibility of one individual. And so how that position, data scientists, exists in your organization is going to determine exactly what they're going to be doing. But for the purposes of this webinar, when I say data scientist, I do mean machine learning engineer, modeling and analytical expert, and data engineer, right? Anyone who would be part of the data science activity inside of an organization.
Okay. So then I've got a couple questions that I think relate, are kind of connecting back to the change data capture idea. This image here sort of is showing this event bus, and so we have one question that's asking, could this just be a simple messaging system like RabbitMQ? And then there's kind of maybe a related question, which is, we're not really seeing here necessarily multiple data sources. It kind of looks like there's one database. But if there were multiple databases, multiple data sources, how do you kind of handle change data capture in the scenario where you have a lot of heterogeneous data sources?
Oh, those are great questions. So in terms of RabbitMQ and stateless PubSub, you can use that for async inferencing, right? So you can use it for what we were talking about in this section. Unfortunately, you can't use it for change data capture and reproducibility, because RabbitMQ and other types of lightweight brokers like Google PubSub and SQS, they don't order the events, right? So they can't be used for change data capture. You need a log-based eventing system like NATS or Kafka or Pulsar or Ensign in order to do the reproducibility part. But for async inferencing, yes, you could use RabbitMQ. In terms of heterogeneous data sources, the way that things are usually architected in the eventing space is that you'll have topics where each topic is a like a data flow, and you can sort of think of it as like a database table. So the simplest architecture is to simply join on two topics from heterogeneous data sources. And so in that case, you would have to keep the start offset and the end offset for each topic that you're joining on, then create a snapshot from each of those data sources, and then train your model. So that's one method to do it, and that scales to however many data sources and topics you would like it to. Another way to do it is to have a DAG, a directed acyclic graph of data flows, right? So you could actually create a process that performs the join of the CDC by listening on multiple data flows, performing that join, and then spitting out another topic that has CDC, and then you could offset on that one. So what it depends on is how flexible you want your process to be, right? If you want maximum flexibility, then you keep things as close to the incoming data sources as you can. But if you want, automated wrangling and maybe a little bit more structure in your data workflows, then you might put in these sort of intermediate data steps, and have these streams connecting to other streams and going to different places inside of your data application. So even though it looks like a single event bus, it's actually made up of multiple topics. And same here, right? You can have multiple models that are working on different topics, operated on by either the same or different applications.
There's a good number more questions. Maybe I'll ask one more, and then you can kind of finish your last section. If we have time, we can do some more, a couple more of these questions. But here's a good one. From your experience, like how mature is MLOps right now in industry? Is this something that like, everybody is doing except for me? Is this somebody that, everybody's talking about doing, but nobody's actually doing it? How far along are things now? And like, how will that be different in, let's say, 3 years?
The maturity level is low. The 13% of teams that are getting their models in production have good integrated workflows with the software engineering teams, which usually means that they are part of the software engineering team. And to me, that means that they're not doing MLOps. What they're doing is product development. So MLOps is immature right now. It is something that everyone's talking about. I don't think anyone's really got a good handle on it. 3 years from now, I would really like to see that 87% number drop, right? And I think that we as a group know of the opportunity of predictive systems to be used in applications to do a great number of very beneficial things, but they can't do that if they're not being used. So we need to get that 87% number down. All right, so I really want to quickly go through this last section, which is monitoring and triggers, which is probably what most people think of when they think of MLOps. And the thing that I would like to encourage everyone to do is, rather than spend a ton of time, in the model selection process trying to find the model that's right and wait and don't get into production, instead deploy those models. And as long as you have monitoring and explainability, those weak models can be used. And what you guys will find is that models will benefit from application-specific feedback and from training data beyond those initial data sets. The other thing to note, though, is that models will decay over time. You can't just release them in the wild and expect for them to last forever. So they do need to be trained on new data, and that we need to ensure that they are correctly generalized to the application they're being used in. And of course, more data beats better algorithms, right? The models that are being used in production benefit from the possibility of new features, not just new instances, but new columns as well. So what are we monitoring and how do we get feedback? Well, things that we should be monitoring are how long does it take to make an inference, cross-validation scores. So we want to make sure that we are routinely cross-validating our models, not just at the beginning and have some initial scores. We want to keep doing that over time. We want to be watching instance distance from the centers, right? So new instances are coming in, we're making predictions on them. Are they generalized or are they out of the side of the scope of the main training data? And we want to think about the amount of relevant data that is coming in, right? Are we making good predictions, yes or no? And all of these things create the opportunity for triggers, right? Can we create alerts or thresholds to trigger ML operation responses to a live model that's being used in production? And of course, triggers are events, right? So just as a re-architecting of this idea, if we have our instance stream coming in, our model is making predictions on them. It can be routinely cross-validated using that same instance stream and sending out metrics, right? The metrics can be observed inside of our model management tool. We can use our results stream not only to go to the application, but we can also, if we have annotation, if we have human annotators that can like thumbs up, thumbs down, different predictions are making, we can enhance our training data sets. We can engage in active learning, which is human in the loop learning. And then now we have a label stream and metrics that allow us to say, do we have enough data to retrain our model? Can we decay data and train our model on sort of a new set of data, and make sure that we are keeping our models strengthening over time and engaged with the application over time. So the last point I want to make on this is, obviously data flows are important, but it also gives us the opportunity to think about what kinds of models are right for data flows and for MLOps. So the first one I want to point out is that online models, right? Things like Bayesian models, naive Bayes, or different types of AdaBoost, or one dependence estimators, or Bayesian networks. But these can all be updated online, because under the hood, what these things are doing is just maintaining a truth table, right? Maintaining a probability space. Multi-armed bandits and other types of reinforcement learning are designed to be trained as they are making predictions, and can be updated without retraining. So often, you might be making decisions about what models to use based on your MLOps opportunities. But it also gives you an opportunity for active learning, right? Human in the loop training pairing with model diagnostics, particularly visual model diagnostics, can help you really get to that model selection triple faster, right? What model is going to work in the end. And then, of course, some models, you just have to do batch retraining, right? Like that does happen, but you can use these triggers to determine like when do we trigger a batch retraining cycle and evaluate it, and you can automate those cycles, which is a lot of what I used to do in the past, was automating the models and the retraining cycle, so that the data science team didn't have to be involved in that process. So, in the end here, right, what we want to do is we want to rethink our machine learning operations as data flows, because if we design systems that reflect the communication structure of our organizations, then data flows allow us to facilitate our communication with other teams, with the product team, with the data team, with the software engineering team, with the DevOps team. And I think that if we can do that, that's how we will reduce this 87% of models never get into production number, by directly addressing the problems that come with getting things into production. So I know we just have a minute left, but I'll take some last questions, but I just want to sort of follow up by saying, we want you to explore and experiment. We have a data playground at rotational.io. So go check out the data playground if you want to get access to some data flows that are live. And of course, you can always contact us if you have a specific architecture question, or if you want to go over what you're doing for MLOps, we'd be happy to chat with you about it. I'll turn it back over to Rebecca.
Thank you so much, Benjamin. And I was able to respond to a couple of the remaining questions just based on your prior answers. So I think we maybe we're square with everyone. I guess there's two notes that we do want to make, which is that we have another webinar coming up on August 1st, which is kind of thinking about how getting models kind of up and running works when your model is a language model. So if anybody is sort of looking into large language models, or just generally has a lot of natural language processing tasks, I think this would be a really neat one. We're going to be talking about an open source library called River, and talking about Hugging Face and some of the ones that I think a lot of people are experimenting with now. And then we have a wait list for MLOps 201, which will kind of help those of you who are ready to kind of like get started and kind of start tinkering. You can join that, and we will get you started. Thank you all so much. Thank you. Big round of applause for our speaker, Dr. Bengfort. Thank you so much for sharing your wisdom. You know, it was wonderful to have so many people join from all over the world, from Sri Lanka and Turkey, Edinburgh, Virginia, Chicago, all over the place, Iowa. So thank you all so much. And we hope to see you at the next one.